Alright, so use the following information to calculate the hydronium ion concentration in a sample of lake water, titrated using a standardized solution of sodium hydroxide. Alright. Are you good? You okay? Okay. So it's given us a bunch of information here. We want to calculate, what do we want? It says using the information to calculate the hydronium ion concentration in the sample of lake water. So let's label all this stuff to use this formula. So we've got our formula: C acid, B acid, C base, V base. So our concentration of our hydroxide ions, we've got hydroxide, which we're comparing that to. Our hydroxide is OH. You don't remember that one. So this would be our base. So this is a concentration, so that's going to be our C base. The volume of lake water that we have, our lake water is what we're trying to find out. And hydronium, if you don't remember, do you remember what hydronium is? Hydronium is H3O plus. And that's what we're talking about when we're talking about acids. Hello? Okay, sounds good. Bye. Nina, so you're picked up. You okay? You'll have to watch this. I'll post it after this. I hope you feel better. See you tomorrow, maybe? Okay. Alright, so continuing on. You're going to hear that random conversation in the middle. The hydronium is our acid. Okay? So the hydronium is what we're trying to figure out the concentration of, but they're telling us our lake water has an amount of 10 milliliters. So this is going to be our volume of our acid, because our lake water is our acid. Do you have this as an example that you're ready, or you just want to pay attention? Okay. So hydroxide ions, that's our base. Our lake water is our acid. And then this is our reading, our initial and final. That's using this. So you write down where it starts and where it stops. So really that's not two numbers. We just need to minus those two numbers from each other to figure it out. So we always take our final minus our initial for our readings. So our final reading is 12.13 minus our initial, which is 2.25. So can we, do you need your calculator again? No. Here, Nevis, did you just sanitize first? Sorry, thank you. So 12.13 minus 2.25. See, you just, what do we get? 12.13 minus 2.25 is 9.88. Right? That's what you got? Okay. And that's in milliliters. All right? So that milliliter amount is our burette. Our burette is holding hydroxide. So this number is our volume of our base. All right? I'm going to write all this out on the bottom here. Sort it out. So we got V acid, C acid, B base, C base. Okay, so I'm just going to write down what I've got from the top. So our V acid, I said, is 10 milliliters. we got to change that, right, into liters. So how do we change 10 milliliters into liters?
Divide by 1,000.
Divide by 1,000. Perfect. So if we divide that by 1,000, we will get our liter amount, which 1, 2, 3, so 0.010, right? Our C acid, we go back to up here. Do I have a C acid? That's what we're trying to find out. So we don't actually have that. That's our missing piece. So I'm going to put a question mark. Our V base, the volume of our base, they've told us is, we calculated it, right? 9.88. So we write that down here, 9.88. We need to change that to liters as well. So what do? Divide by 1,000, right? So 9.88 milliliters would become 0.0988 liters.
Wait, are we finding our C base?
We have our C base up at the very top. See?
Okay.
C base is 0.000125. So our missing piece is our C acid. Formula. V acid, C acid is equal to V base, C base. And then you want to plug in all those numbers. Did you already do it? Kind of. So our V acid is 0.010, right? That's what we found up here. Our C acid is, that's what we don't know. That's our missing piece. So I'm going to write C acid in the bracket. It's equal to our V base, which we've known as being this. And our C base, we know as 0.000125. Now what? Times the one on the right. Did you get an answer for that?
0.00012. Or 0 and 12.
So I got 0.00001235. You got the 35?
Just 1, 2.
Okay. Maybe yours rounded for some reason. I'm using my iPhone.
Yeah, there we go.
Why did my iPhone have more digits than yours? Anyway, not important. It's really not going to change much in the long run. So then we still got our, on the other side, 0.010, and then our C acid. So next step.
We divide V acid by base.
We divide by 0.010. I don't know if that's what you meant. And then what do we get as an answer? Did you do that out?
Yep. 0.0012.
Yeah. So 0.0012. I got 35 as well. Because I have those extra digits. But in the long run, our final answer should always be in 2 decimal places of numbers I would prefer. So Kelvin, yours is good at that. But it's really important that we write our units. So our units, what does this number even mean? Well, go back to the first question. calculate the hydronium ion concentration. So this is a concentration, which means what's the units for it? You what?
Wait.
How do we measure concentration?
What's their base? Was it ml?
It's not milliliters. It's moles per liter.
Oh, okay.
So you can write moles per liter like that, or you can write big M. Okay? Big M means moles per liters. Okay? So whatever one you want to write. Okay? Okay?
So basically it's math.
It's math.
Basically.
Chemistry is math. Like applied math. That's why I like chemistry so much.
Math kind of scared me last year.
Is it?
I'm not sure if I'm good at it.
I think you're fine at it. You just did this one, didn't you?
Yep.
You're good at science now. So there's there's one practice question that goes along with that, number 42 on page 211. I don't know, is it written there for you? It should be?
Yep.
Perfect. So that one, we're just gonna skip past that. So do that one after.
Wait, it says 42 to 44.
Yeah, I only want you to do 42.
Okay.
So follow whatever it says on your thing. I'm trying to make it a little less. All right? So just do 42, don't do 42 to 44. All right? Now there's a little bit more I gotta go through. Say a little bit, seems like a lot, but hopefully we can get through it quickly. Strong and weak acids and bases. It says two solutions can have identical molar concentrations, but have different pH. So two solutions could have the same concentration but different pH, and this all has to do with the amount of H3Os in it. So this H3O is what determines your pH. So pH is really just measuring, if I wanted to find the pH of my orange juice, it's just saying how many hydronium ions are in there. The more hydronium ions, the more acidic it is. Okay? The strength of an acid or a base is determined only by the extent of which an acid or base will react with water to produce hydronium or hydroxide. So if something is basic, then it has lots of hydroxides. The strength of an acid or a base can be determined by the position on the table of acids and bases. So if you go to your data booklet on page 12 of your data booklet, the green one. Go. Get your data booklet. Okay. Go to page 12. On there. This page, on page 12 at the top, that table is going to tell you the strength of an acid or a base. Okay? So, just to show the people that are on this video, go to page 12 of this. Oops.
Which one's the strongest one? Hydrochloric acid?
Yes.
How strong is that?
Strongest of all the acids. Nothing is stronger. So yeah, the strongest acid is going to be at the top. It says on the side, on the left-hand side, it says increasing strength of acid. So the higher up it is on the table, the stronger the acid. And then the lower it is on the table, the stronger base it is. So as you go down the table, you become a stronger base. So you're either a stronger acid or a stronger base.
So
Okay.
water is the strongest base?
Water? hydroxide. So see the bases are on the second column. OH is the strongest base at the very bottom. Okay, so that's that. I'm just going to continue on. So there's some practice problems that go along with that as well. I guess there's no examples of that unless it's right here. Why are they giving us another practice problem like this? On titrations, we just did one like that. Another titration. Some more practice problems. Buffering. Okay, I'm just gonna skip right to here. All I want you to know is that you're gonna have to use this to figure out which one's stronger acid or base, and you've got that table there. I'm going to skip those examples on concentration or on titration. When you guys are in class or next, we're going to do a lab on that. So these are just practice problems, and I can do those ones and post them on the classroom, but I'm not going to go through those right now. We just went through an example that was exactly the same back here. Okay, so this example is the same as these two I'm skipping. So we're just going to talk about buffering, and that'll be the end of this chapter. Okay? So buffering. What does buffering mean? We talked about that the other day in 1.3. Buffering means to sort of make something less acidic. A buffer refers to the ability of a substance that's exposed to an acid or a base to not experience change in pH. So if I put an acid on your skin, if you had something on there that was basic, it would make it so that the pH of your skin didn't change. Carbonate is a common buffer in soil and in water. And that's what we were talking about the other day. Remember how all the prairies has a really good buffer?
Wait, is hot sauce an acid?
Yes.
You use milk, adding a base, right?
Right.
Hey.
There you go. There's a real life example. That's great. Do you like hot sauce?
Yes, I
I love hot sauce. I put hot sauce on everything. So hot sauce, great example. Your mouth is spicy, it's hot. You need to neutralize it, use milk. Milk is a base. It'll help. There's also protein in milk that blocks where your receptors of your taste buds are tasting the spice. It actually blocks that, which makes it less spicy too. Yeah. So, but in hot sauce, a lot of hot sauce has vinegar in it, so that's an acid. So there's acids definitely in there, and then that spice component makes it acidic. So there you go, perfect life example of acids and bases.
Wait, citric acid enough to dissolve the skin?
Probably it'd be corrosive. I wouldn't say it would dissolve your skin.
Not right away, of course. How about over time?
Over time, for sure. So don't bathe in orange juice as I'm drinking my citric acid.
You're telling me a lot of great ideas for one of my inventions.
What, bathing in orange juice?
No.
Okay. Anyway, let's finish this thought. So it says buffering in living organisms. So in our bodies, your blood contains carbonic acid and hydrogen carbonate. And both of these help to buffer excess acids and bases in your blood. So if you take things into your body that are acidic or basic, your blood is going to work to neutralize it. This is important because even a change of 0.5 in the pH of your blood can be fatal. So a change in your blood of 0.5 pH, you can die. Yeah, so like drinking acid, for instance, not going to be good. That's why you would die. All right, so that's why it's really your body's always working out all the time to make sure that you're staying stable inside. And what's what's doing that is our carbonic acids and our hydrogen carbonates.
Orange is fatal.
No, it's not going to change it that much because we have those things in our blood to like fix it. If you drank hydrochloric acid, yes, fatal. Again, I don't know why you're asking these questions. It sounds devious. Last one, second last one. So this shows you what happens in your blood. So your red blood cells, you've got these acids and bases in your blood, and they will work back and forth. So you've got your acid plus your base will give you hydrogen carbonate, can't say that, and your acid. So it's just working back and forth to neutralize. So it's like, oh, we've got an acid in our blood, let's add some base. Oh, we've got some bases in our blood, let's add some acid. So your body's always working to keep it level. Note, buffering does not last forever. Eventually all of the buffering systems, I think this is over top. Where's the blue? Okay. What does it say here? Eventually all the buffering material will have reacted and the pH of the system will change. So we try and add acids and bases together and it's like, okay, we're good, we're good, we're good. Once we run out, well, the buffer's gone and it's just gonna turn into an acid or a base, okay? So we don't have unlimited amount of buffers. We don't have unlimited amount of buffers in our body. So yeah, maybe you would kill yourself if you drank, I don't know, 100 liters of orange juice, you know what I mean? Like, you only have so much in your body that's gonna be able to protect you, and once it's used up, well, that's the end.
Well, it's gonna be a long assassination mission.
Okay. Also, that's when we talk about the soil, remember we have carbonate in the soil that neutralizes, but there's only so much of it, right? So once it's used up, well, now our soil is acidic. Okay? That's it. That's the end of that section. That's not too bad, is it? You just had to do one type of calculation and try to do those practice problems that go along with that. Yeah.